Okay, so let's get started. I need to start with apologizing for last lecture. It was surely not my intention to steal 15 minutes of your valuable lunchtime. It's just when things happen like this, my standard excuse is I am a professor, and therefore I'm allowed to be completely off target sometimes. You know, like confusion is a hallmark of a professor sometimes, and I was really confused about the clock management last time. So I do apologize for that. Next time this happens, you know, feel free to somehow indicate slightly that I'm running over time, and I will do something like that. I was wondering why people were starting to leave the room. So, but you need to be even more clear than that and say, okay, how about wrapping up now because the lecture is over? And that's fine. I don't mind. Absolutely not at all. So with that, I'm sorry. Hopefully it won't be happening again. So today we will continue to talk about the physical layer and hopefully wrap that up today, at least the modulation and demodulation part. And then next week we'll go into error detection and then start to talk hopefully a little bit about retransmission protocols at that time. So what we did last time is we talked a little bit about constellations and how constellations, that is sets of amplitudes when it comes to pulse amplitude modulation, how that affects the energy of the transmitted pulse. And if we think of the data as being random, then the amplitude that we send is also random, and the average signal energy is then the expected value of the random transmitted energy. And it can be written as the product of EH and EA. And EH is just the energy of the pulse shift that we use, and EA is the energy of the constellation. And it's the amplitude which is a random variable because it's driven by the random bits that we transmit over the channel. So the energy, constellation energy, is the expected value of the amplitude magnitude squared. Okay, and when all these pulses, rather all these amplitudes are equally likely to be transmitted, and that is the case when the bits that they correspond to are also equally likely, zeros and ones. This is the standard assumption. If that is that assumption is valid, then this one evaluates to this one. If it's not valid, then the expectation will become something else. Okay, but in this case, in this particular case, then it's simply like this. We just take the each individual amplitude, we square it, we add them together, and divide through by the number of possible amplitudes. Okay, so we can think of this as, you know, the average squared amplitude that we use on the channel. Okay, and we call this the energy for the constellation. And then we saw that given the energy per symbol, we can say something about what is the transmit power we need. How big of a power amplifier do we need at the transmitter side? So the power, in general, power is related to energy through time. Okay, so P is equal to E divided by T. This is a classical equation that shows up in many different shapes and forms. In this context, since this is the energy per symbol, what we should divide through by here is the time between symbols. Okay, so another way to say that is that the power is the energy per symbol multiplied with the rate for symbols, the symbol rate. Okay, so power increases if the energy per symbol increases. That makes sense. The power increases also if we are transmitting symbols faster. Okay, because then we are spending more energy per second. Okay, so hopefully this equation makes intuitive sense. And then we show also that power can be written as ES times RS, if we like, or EB times RB, where B now stands for bit. So EB is the average energy per bit that we use, and RB is the data rate, the number of bits per second that we transmit. Okay, and RB is of course related to RS through the log 2 of m, which is the number of bits that we transmit per symbol. Similar here, EB is related to ES. So ES divided by the number of bits per symbol gives us EB. Okay, so not so complicated equations. All right, so we talked about that, and now we know a little bit about how to calculate ES, and we will see later on that ES plays a key role in figuring out what the error probability will be at the end of the day. Another thing, and also to compute then the error probability here, we typically model the noise as white and Gaussian. So we will be interested in Gaussian probabilities here. And we'll just introduce some notation for the tail of the Gaussian bell curve. We call that the Q function. So if we have a Gaussian random variable with mean mu and sigma, variance sigma squared, and we want to calculate the probability that that exceeds some number z, we can use the Q function, which is implemented in MATLAB. It's essentially the tail. It is the tail of a Gaussian bell curve with mean 0 and standard deviation 1. So we just take z minus mu and divide through by the standard deviation. And this is the definition of the Q function. In particular, if we have something which is 0 mean, okay, so a Gaussian random variable with 0 mean with some variance, then if we want to calculate the probability that that exceeds some number, is the same due to symmetry to say that we want to compute the probability that the Gaussian random variable is less than negative z. Okay, and that's just because the Gaussian curve is symmetric, so the right tail is equal to the left tail. It's easy enough to see. And both of those can be computed in terms of the Q function as Q z divided by sigma. And we will actually use this relationship a little bit later today. Okay. So back to the issue here. We are trying now to characterize the performance of pulse amplitude modulation when we are transmitting over a noisy channel. Okay, so we have our now hopefully rather familiar block diagram here. And the noise here, we model that as white Gaussian noise. And another way to say that is that the channel that we are considering is an additive white Gaussian noise channel, or AWGN for short. Okay, so white Gaussian noise, what does that mean? Well, it means that the noise has mean 0. Okay, so it doesn't have a, the average is 0 of it. And it has a autocorrelation function Rn, which is just a scaled delta function. That is the whiteness condition here. And the constant in front of this delta function, n naught over 2, is quite, why n naught? Why divide by 2, right? It seems strange. Why not call this k or something like this for constant maybe? So this n naught over 2 has, for historical reasons, always been there. Okay, so you see that in every book. So we will use that notation too, right? But the important thing at this moment is to say that the autocorrelation function is just a delta function. Okay. So let's continue here now a little bit. So the channel noise, N of t, is assumed to be white and Gaussian. So in particular, that means that it's a zero mean process, so there is no average. And the autocorrelation function then is this n naught over 2 times delta of t. Okay, so let's look a little bit closer to this, so what can we say about the autocorrelation function when t is not equal to 0? What is it? 0, exactly. So outside t equals 0, sorry, maybe it should be tau here. It doesn't really matter. Okay. So what this tells us, this condition tells us, is that the process is completely unpredictable. Meaning that if we knew the noise process up to some certain time here, what is it in the future? That's a question of predictability, right? So if the autocorrelation function is of this nature, it implies that even if I knew exactly the amplitude of the noise at this point in time, and maybe for all eternity before this point in time, it tells me exactly nothing about what it is in the future. There is no predictability left. So it's not smooth like this at all when it's a white Gaussian noise. It goes all over the place, right? So there is no correlation between points as we go along in time. Okay? So completely unpredictable. Yes?
There should be inequality there. Inequality.
Thank you. Like this. Okay, so now we only have 1 point left, right? So what is the autocorrelation function when tau is equal to 0?
And 0 over 2.
Nope.
Oh.
Good guess, but wrong. Nobody dares? No? Infinity. Right? And why is that? It's because the amplitude of the delta function, it's the Dirac delta function, not the discrete one. And it has infinite amplitude.
Oh.
Yeah. Yeah. So, what does that tell us? It tells us also that the amplitudes here are infinite. Right? So can we imagine something worse when it comes to a disturbance? I claim not. Right? It has infinite amplitude and is completely unpredictable. So that's pretty bad noise, I would say. So the question is everything hopeless now? Luckily not. Okay. So the magic thing here is that by processing the noise, okay, so the noise goes through the chain like this. It goes down and it goes through this filter and so forth, and then it ends up at this point when it's time to make a decision. Actually, even though the noise here has infinite amplitude, is completely unpredictable and so forth, when we filter it, it becomes much more well behaved. Right. It becomes now a smoother process, but more importantly, it has now finite amplitudes. Or actually, since it's a random process, we're more interested in its variance. And that will be finite. Okay, so that's actually a little bit surprising, but let's prove that fact. Okay, now so what is this? I forgot to write this up. What is the autocorrelation function? It's basically to take the process and then we multiply it with the process. Advanced in time by tau seconds. So when we put in tau equals 0, we get the expected value of n squared. So it is sort of like the variance of the Gaussian process. And that turns out to be infinite in this case. All right, so let's filter. So we have n of t, and then through a filter. And it turns out that the impulse response of the filter, its shape is not super important. It's some other property of the impulse response which is important, namely its energy. So instead of writing h conjugate negative t for the matched filter, we'd just take a generic filter, and let's just call it h. Okay, and then we will have some output here, Wt. Okay, So what is WT? Well, we know what the input is and we know the impulse response. We can just convolve these two things and get the output. So WT is N of t convolved with H of t. Okay. And we can write this as an integral from minus infinity to infinity of n u h t minus u du. Right? It's just a definition of convolution. Okay. So we know that n here is Gaussian. It's a Gaussian process. So it's a sequence of Gaussian random variables. So what can we say about W? What is the distribution of W? Okay, so let's figure this one out in steps. I want you guys to help me out here. Okay, so this one is Gaussian. It's a Gaussian random variable, right? So what happens if I take n of u and multiply that with this one? For a given t and u. So this is just a number, right? For a fixed t and u, this is just a number. Agreed? And then I multiply that with a Gaussian. So what is the distribution of the product of a Gaussian with a constant? So the question is, if I have a Gaussian random variable and I multiply with a constant, what is the distribution of the product? Gaussian. Gaussian, great. So not only is this Gaussian, but the whole thing is Gaussian. Okay, so what happens if we integrate then a Gaussian process? Well, integration, what is that really? Well, it's a sum, right? It's a limit of a sum. So we can think of this as being a sum of Gaussian random variables, the whole thing, right? So if you're unconvinced about this, make this into a Riemann sum, right? And then you see it's the integral in itself is a summation, right? So what is the distribution of a sum of Gaussian random variables? It is no, the distribution. The mean is 0, I agree. The distribution. So if you take two Gaussian random variables and add them together, you get what? A Gaussian random variables. If you get 3, it's Gaussian random variables. The whole thing becomes Gaussian, which is excellent for the math of this because it makes everything simple. So the whole thing is Gaussian, which means that this is a Gaussian random process. Okay, so this is great. What is then the, if we fix t to be some, we look at some specific t here, and let's figure out the distribution for this one. We know it's Gaussian, so what do we need in order to specify the distribution of Gaussian random variable? We need two things. We need the mean, and we need the variance. And let's start with the mean. So the expected value of WT is simply the expected value of this integral. And expectation is a linear operator, so we can move that inside the integral if we like. Okay, a mathematician would not do this without a lot of precautions, but we are fearless when it comes to math, so we'll just do it. Okay, so it's going to be minus infinity to infinity of the expected value of the integrand. There is one thing in the integrand which is random, namely the noise. The h here is a deterministic function, so we don't need to take the expectation of that. So we have the expectation of n of u times h t minus u du. Okay, And we already know the answer. So what is the end result of this? Well, we know that the expected value of the noise is the average of the noise. We know that that is equal to the mean value of the noise is 0, right? 0. So the whole thing is then 0. Okay. Good. So now the mean is over with. So let's figure out then the variance. So since the mean is equal to 0, the variance is also the second moment. So basically we take the random variable, we square that and take the expected value of that. Okay, and we continue to do this in the same way. It's the expected value of a square of t squared. And what is w? Well, w is this integral, so let's just write this as a double integral. So then we have the expected value of the integral from minus infinity to infinity, n of u, ht minus u du. And then we need another integral from minus infinity to infinity. And now we choose v as our integration variable. So n of v ht minus v dv. It should be the same t in both integral actually, right? Because what we do is wt squared. Okay. All right. So then let's reshuffle a few things here and move in the expectation. We can write this as a double integral. As follows. Take one integral out and then bracket and then integral, and the inner integral is here over u, and we have the expected value here somewhere, and now we need to put in everything inside the expected value here, which is random, and we have two things which are random here, nu and nv. So these should be put inside here, nu and v. And then we have the rest of the integrants, which is the h components here. And we have ht minus u and ht minus v. Okay, so let's close the integral, the inner integral. Let's make that over u, and then we have the outer integral over v. So it's like this. Okay. So what we want to do now is to look at this thing here. Do we know anything about this expression here? The expected value of nu times nv? So what do we know? We know something about this one, the autocorrelation function, which is the expected value of nt plus tau. Okay, so we see that the autocorrelation function is the expected value of n at some time times the expected value times the process at some later time. So from this, we can easily rewrite this in terms of that. Okay. And it doesn't take too long looking at this to see that this, what we have here, is simply the autocorrelation function now at the difference between the argument of the n functions here, right? So it's going to be v minus u or u minus v. It doesn't matter actually. But we see that if I take the argument here minus the argument here, that's my tau, right? So I take v minus u, and that is my tau. Agree? Okay. Great. And why is this great? Because we know what this is. It's n naught over 2 times delta of tau, which is now u minus v. And here one gets very, very happy when we see this, because now we have a delta function, and a delta function makes integration so much easier, right? So what we need to do now is we can simply evaluate this integral immediately, because we have a delta function times another regular function here, and we integrate over u. So what we need to do is to figure out when does this delta function become non-zero. For what u does it become non-zero? When u is equal to v, exactly. And that v value we plug in to here, and that is the end of that integration. Okay. So what we're left with here is the integral, and the whole thing here in the middle becomes then n naught over 2, which is the scaling factor in front of the delta function. And then the rest of the integrand, h, where u, we replaced u with the value of u that makes the argument of the delta function 0. In this case, u equals v. So here we get simply ht minus v. Okay, so that's the inner integral, the value of that. And then we have ht minus v at the outer integral left, and then this should be integrated over dv, over v. Okay, so no more delta functions, so here we actually need to perform this integration. So we simplify this a little bit and write this as n naught over 2 times the integral from minus infinity to infinity, and here we see we have h squared t minus v dv. Agree? Right. So what is the value of the last integral here? Very good. So this is the energy of H. Okay, so all right, we have shifted the H and so forth, but since we integrate over all time, we can do a change of variables, and here we see it's the integral of H squared for all times. So that's the energy of H. So the end result here is surprisingly simple, that the variance of the noise is simply n naught over 2 times EH. Okay. So n naught over 2, what does that come from? Well, it comes from the specification of the channel. So n naught over 2 is a channel parameter. The greater n naught is, the noisier the channel is. Where does EH come from? Well, it becomes from our choice of impulse response. And you see here, it was okay for me to not flip this impulse response and conjugate that, because it doesn't really matter. The only thing that matters is the energy of the impulse response of the filter. And the energy of this is equal to the energy of this one, which is EH. So it's the same. I just saved us some writing here. Okay. All right. So now that's great. So what we know now that is that at this point in the diagram, we know what the noise is, and then we sample that, and then we get one noise sample, and we know that that noise sample is a Gaussian random variable with 0 mean and this variance. Okay, and then what we do then is to divide through by the energy of H, and then we here have the input to the slicer, all right? And then we need to figure out what is the probability that the slicer outputs the wrong value. Okay, so that's our next step. Okay. So I think we're going to do like this. We're going to continue on this whiteboard here. So now we're going to compute the error probability for PAM. So we're going to transmit just one single symbol and calculate the probability that that is in error. And since all symbols will be treated in the same way, that is actually the error probability of any of the symbols that we transmit. So we're going to transmit one symbol. So the received signal then is our transmitted amplitude, which we don't know. This is the one that we want to figure out. And then it's multiplied with the pulse shape, h. And plus this, we have the noise. Right? So this is the received signal. And the key is then to try to figure out what A is. And we use the minimum distance receiver to do this. Where this A is inside the set curly A, which is the one of the amplitudes. We don't know which. Okay, and we assume that we transmit these symbols equally likely, so there is no preferred amplitude, right? Actually, when there is a preferred amplitude, that makes our life easier. So this is actually a worst case assumption in some degree. So the match filter output what is that? Well, we denoted that by y. Okay, so this is the sample of the output of the matched filter at time 0. And what is the output of the matched filter? Well, it's the input is the received signal, and then it's convolved with the matched filter impulse response. And that is the conjugate of h and then time reversed. Okay, input, matched filter. Okay, and we're interested in the sample at time t equals 0. So we are interested in just a single sample, not the entire pulse here. Okay. So what can we say about R? Well, R is equal to AH plus N, so we can separate that into two components. One which is due to the signal that we're after, and one which is due to the noise, which makes our life difficult here. So let's continue here, and we can write this as the convolution of A times H convolved with the match filter impulse response sampled at time equals 0 plus the noise convolved with the matched filter sampled at time equals 0. Okay. And let's start with the second term, the noise term here. What do we know about this? Well, it's Wt when t is equal to 0. Okay. And what is Wt? Well, it's the filtered version of the noise. So we know that this is a Gaussian random variable, so which has average 0 and a variance. What was the variance? Well, it's n naught over 2 times EH. Okay, so we know the noise sample, we know it's a Gaussian random variable, we know its variance. What do we know about the first term here, the signal term here? Well, if we go back a lecture or two, we see that this, actually the pulse convolved with its matched filter impulse response sampled at time equals 0 is simply the energy of the pulse. Do you remember this? If not, you could just go back and look at that. It's not difficult to show. So this is equal to EH. So at the end of the day, we have a very simple equation for y. Y is simply A, the amplitude whose value we don't know, times EH plus this Gaussian random variable W. Okay. So let's go back and look at the block diagram here quickly. What we have done now is that we have looked at the receipt signal, we processed that with the matched filter, and we sampled that. So now we have characterized what y is. Y is equal to what we transmitted times EH plus W, where W is the noise contribution. So the next step is to simply divide by the energy of H. And then the input here would simply be Y divided by the energy of H. I mean, that's what it is, right? And that turns out to be the transmitted symbol, the one that we are looking for, plus a scaled version of the noise. W divided by EH. Okay. So the input to the slicer is also known as the decision variable because it's the variable that we base our decision on. So the decision variable i.e. the input to slicer let's call that Z. So that's Y divided by EH, which is then equal to A plus W divided by EH. And let's call W divided by EH for N, for the noise sample. And what can we say about the noise sample? Well, it's W divided by EH. W we know is a Gaussian random variable with a certain mean and variance. So what can we say about the noise? Well, it's also a Gaussian random variable because it's a Gaussian random variable divided by a constant. That's still a Gaussian random variable. Good. So we know it's Gaussian. What is the average of N? The mean of N? Still 0. W has average 0, right? Mean 0. So N must also have mean 0. Take the expected value left-hand side and right-hand side. You see it's going to be 0. Okay, 0. Good. Variance. What happens with the variance? It's not hard to see that if we have a variable and we multiply that with the constant, then the variance changes with the product, the square of the constant. Okay, so it's like if you multiply something with the a random variable with the constant, the variance scales with the square of the constant. Okay, so it's almost like amplitude energy, right? So what do we have here? We have n naught over 2 times EH. That's the original variance of W. And then we divide through by EH. That means that the variance should scale with 1 over EH squared. Okay, so times 1 over EH squared, like that. And let's clean this up. So this is just a Gaussian random variable with 0 mean. And then we see that the one of the EHs cancels. So we have n naught over 2 times 2 times EH. That's the end. That's the end result of the variance. Okay. So now we've done all the groundwork for being able to compute the error probability. We have characterized the statistical property of the input to the decision device. So this is our decision variable. So we know it's going to be the amplitude that we look for plus a noise variable. That noise variable has 0 mean, so the mean won't help us, right? And it has a certain variance here. And we see that the variance here depends on n naught and also on the energy of the impulse response. Okay. So, now, suppose we are looking at pulse amplitude modulation where we have this standard type of constellation. So when A, curly A, the set of the amplitudes is equidistant from each other, and we have capital M of those. So A is, say, plus minus C, plus minus 2C, and we continue up, and the outermost points here are plus minus M minus 1 times Z. Okay. So, for instance, when M is equal to 8, the constellation would look something like this. We would have, say, the origin here in the middle, and then we go C to the right and C to the left, and then continue 2C to the left and 2C to the right, and then we continue out, and the leftmost point here is negative M minus 1 times C, and the rightmost point here is M minus 1 times C. So these are our constellation points in general, right? Now I wanted to do this for 8, so just to make things a little bit more concrete. And if there is 8 points, there should be 4 points on each side. So we have here C, 2C, we should have 4C, and one more 6C here, and then we should have negative 4C. This is all screwed up. Okay. Let's continue. Let's try this again. Sorry. We have negative 7C, negative 5C, negative 3C, negative C, C, 3C, 5C, and 7C. Okay, so these are the constellation points. Sorry for the confusion here. Okay, now the decision regions here are defined. Okay, so here are the possible transmitted amplitudes, right? So this is the constellation. What we have done now is that we have transmitted one of these points. We don't know which one. So the receive point will be the transmitted point plus some noise. And sometimes the noise makes it so that we get closer to some other signal point than the point that we transmitted. And that gives us an error. And remember that this is the, if we think of this as the decision variable axis here, some of these, we have decision regions on this axis. So every point to the left of the border between 7C and 5C will be decoded to 7C, right? And the border between 5C and 3C is negative 4C, so I'll just put in the decision boundaries here in the middle. But now I think we need a break. I'm just messing up this block diagram for you. Okay, so let's take 15 minutes.